Thanks, everyone. I hope you had a nice conference, and thanks for joining me on your Saturday morning, afternoon, evening, or maybe Sunday morning if there's some folks in Asia staying up very late, or if you're watching online in the future on YouTube. I'm going to try to keep an eye on the Q&A in Zoom as well as the channel in Discord if anything kind of comes up along the way to answer. And of course, I'll be in the Gather Town after for questions. Uh, just get my remote working out. There we go. So I'm Roth Michaels. I'm a principal software engineer at Native Instruments, which is a company that makes hardware and software for digital audio. So everything from mixing and mastering records, producing beats, DJing, film, television production. So for this talk, a lot of the examples I'm going to give are going to be kind of based on the idea of digital audio or making things for music production, but you don't need to understand audio or DSP to understand these simple examples. And a little bit of context, working at Native Instruments, this is a company that I actually joined via iZotope and is actually a merger of a number of different audio companies, and which means we have multiple, about 20-year-old C++ code bases. So in my day-to-day work, I get to see C++ written in a lot of different eras, but we're not going to talk about that past stuff today, but we get to talk about kind of what we can do for kind of the latest and greatest when we're writing new C++ code. So why did I want to give this talk? It was inspired by my favorite interview question, which was something that my current my manager asked me when she was doing my initial phone screening when I joined iZotope. And that question is to rate myself as a C++ developer on a scale of 1 to 10, but the number is less important. And then after saying your number, describe what one thing is that someone more junior than you might not know yet about, and that's maybe something that you could teach them. And what's something you don't know yet that someone more experienced might know, and that's something you might want to learn more about. And so often when I get the answers to these questions, when I've been interviewing people, because I kind of stole this question because I liked it, often people are telling me they want to learn more about templates, or they might say template metaprogramming, or maybe something about, I don't understand how partial template specialization works. Or I've heard of this thing called SFINAE, which stands for substitution failure is not an error that's used in metaprogramming. I don't really get how that works. Or I might have seen an example, but don't understand why it works. And so why I was excited to give this talk is we don't need to teach this stuff anymore. There's actually kind of a lot of nicer new ways we can do these things with modern C++ 20 and maybe some more stuff coming later in C++ 23 that lets us write things that used to be in the kind of arcane knowledge of template land that seem much more like normal C++. I'm going to mention a little bit about old school template metaprogramming. If you want to know more about that, there's this great talk from Walter Brown I would suggest you check out. And that slide got spaced in the wrong spot, sorry. And so our journey is going to start with kind of the original purpose of templates in C++, which is for generic programming. And this is something, and we're going to take this kind of through our journey through templates and constexpr. But you'll see that this is something that probably most C++ developers have kind of seen and probably use in their day-to-day life, is we have this function in the standard library called find that lets us look at something like, in this case, a string, and we're looking from the beginning and end of this string and searching for a comma character. And the same algorithm find can work with a string, or it could work with a vector of integers. And this is because it's actually a template that is templated on the type that it's going to operate this algorithm on. And so this is kind of why templates were added to C++, so we could have write one algorithm and allow it to work on multiple types, even types that the writers of the standard library don't provide, but they work on your types as well, as long as they have some comparison operator. But along the way, it was discovered that templates were Turing complete. And I've kind of heard the legend that this was discovered by accident, but it seems like kind of a very smart discovery by someone, Erwin Unruh, I believe, was the first person to discover this. And he was able to discover that with templates, you could write a program. And this program he actually wrote using templates didn't finish compiling, but the result of the program was what was printed in error messages. You could actually, to kind of prove that it's template Turing complete, you can actually make a Lisp using C++ templates. but we won't. Maybe I'll save that for some lightning talk in the future. But to show you some examples of kind of what template metaprogramming looks like when you're writing a function in a template metaprogramming, and that Walter Brown talk I mentioned earlier shows kind of much more in-depth examples of this. You don't actually often write functions, but you write structures that have some template specializations, and then they'll have a member, and that member is the return value of that structure or template meta function. So in this case, to write a template meta function in the kind of traditional way before C++, more modern C++ or postmodern C++, the way you would do it is you'd write a structure like we have at the top for a Fibonacci function that takes some number as a template argument, and it recursively calls itself. And you see that value member is what the return value of this compile time or meta function will be. And then we have two base cases when we get to the bottom of the bit. So we specialize the function, say like, okay, well, if the template argument is 1, return 1 as the value. And if 0 is the value, that's that. And you see if we call it the way you kind of call it at the bottom, where the arguments to our meta function are the template parameter to Fibonacci, and the : value is our return value, which I'm now realizing I've used this slide twice, and the Fibonacci of 6. I'm sorry. I was thinking of factorial. Yes, so Fibonacci 6. Yes, that is 8, I believe. Sorry for getting distracted there. But yeah, as you see, we have kind of the normal meta function and then our base cases. But when constexpr was added to the language, we no longer need to write this kind of more complex way of simulating a function using template structures and specializations of those structures. We can just write a Fibonacci function like this that looks exactly like a normal recursive function. And since it's constexpr, this can compile at compile time, and you see that it works in our static assert. And this is kind of a theme we'll see as we continue through this talk, how new features added to the language allow us to do compile time computation, generic programming, or metaprogramming with things that look much more like standard C++ than lots of template magic with pointing brackets everywhere. And as we've kind of got new language added to the features added to the language, we don't even actually have to write this constexpr Fibonacci as a template if we wanted to operate an arbitrary types T. Instead, we could just use auto here. And now it just exactly looks like a function, even though mechanically it is a template. Or now with concepts, and we'll kind of get into a discussion more what this means, we don't have to just say auto, but we can add in front of this standard unsigned integral. And what this will mean is that the auto type is constrained to only work with types that are unsigned integrals, because this would not necessarily work if you put in a string into this class, this function. And just a few things about constexpr that has gotten a lot better in C++ 20. You can use things like standard vector and standard string and allocate memory inside of constexpr functions, which is new, which allows you to do a lot more stuff. The only rule is you can't have those memory allocations or heap allocations leave the function. So you can create standard strings and vectors inside your function, but you have to return them in some other way that doesn't use that heap memory you used there. And we also have a new feature called const_eval that is a little bit different than constexpr, because constexpr is something that may be evaluated at compile time, and const_eval is something that must be evaluated at compile time by the compiler. So that's we'll leave constexpr there, but you'll see it will kind of come up in other slides later as we use constexpr functions for some things. The other big thing that kind of helps make it easier to write certain things with either template metaprogram or other just templated functions are fold expressions, which gets rid of the need to do kind of tricky recursion tricks that we might need to do otherwise. So this is an example of how to use a fold expression. We can make a function called sum that's going to take some arbitrary number of arguments and arbitrary number of types. And for this to work, they're all going to need to be able to be added together. And you see that we have this template parameter pack so that our argument type args, we have the dot 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 after class or template you could use there as well. And same thing when we're taking the argument args as the type in sum. And in normally, you might do this with some sort of recursive pattern, but now that we have the full expression, which is this dot dot dot, you'll see that this allows us to essentially splat out those arguments. So when we put sum 1, 2, 3, 4, when we have that dot 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 full expression, that will essentially just be adding 1, 2, 3, 4 inside of the instantiation of that template. So it will this code essentially will be transformed in the case of 1, 2, 3, 4 into a function that takes 4 arguments, as the first 2, as the second one, as the second one. And the other thing to keep in mind about fold expressions is they come in 2 forms, one with the dots on the left side and one with the dots on the right side. And that just has to do with associativity. So you see that if I put the dots on the right side, you end up with a number, you add C and D first, and then B, and then A. And just to show you, kind of in a few times in this talk, we're going to look at examples of what this would look like if we were using kind of old school template tricks. I won't necessarily go into all the details, but you'll see here, instead of being able to just say, add up all my arguments, we have to have this recursive function that has a first and a rest and adds all of those until it gets down to the base case of a single function, which just doesn't look quite as nice and simple as this does. And so those are kind of, I just want to briefly mention fold expressions and const expert because they do help make a lot of things that we would do with templates, whether for generic programming or meta programming, a little bit more simple. But the main theme of this talk is concepts. And so that's what we're going to be getting into in the rest of the talk. And that's what that standard integral that we looked at earlier was saying, that we can only do our Fibonacci on integral types. So before concepts, we might have some template function like this foo that we have here that takes 2 template arguments for its argument type and its return type. And with this, there's really no restrictions on what could be passed to this function. You could potentially be using any types, but the designer of this function, you might not have expect every single class type in the world to work with this. In our example of standard find, for your types to work, they have to be comparable. Foo could have some other constraints as well, but you see here, there's nothing that stops you from putting anything you want into T and U. And if some of you might have encountered these sort of errors before, you would get a very kind of complex, tough to figure out perhaps error message about what went wrong. But concepts give you a lot of ways to further constrain and say, no, this type T or U isn't some any particular type, but has some constraints to it. And there's a whole lot of, you normally won't see functions that look this complex, but I'm just kind of showing you this as a brief outline of all the places you can put a concept to further constrain what types your functions or classes and structures operate on. You'll see this appear in a few different places in the further examples. So instead of having class or template T in your template parameter pack, you could actually put a concept name and say this T only can be some type that conforms to a concept C1. And in the later slides, we'll see what it actually means to conform to a concept. You could also do it after the template parameter pack, like say, okay, with this requires statement, and then you provide another concept here, or you'll later see there's also requires expressions we could add here. We could also constrain the return type. Instead of having return type auto, we'll have that auto return type only be things that are valid if they conform to what we're calling our imaginary concept C3. Same thing with function argument types can be constrained to be only C4 in this example. And probably one of the more kind of interesting, useful ones is this last requires that goes at the end of the function declaration. And this is useful if you need to compute something about the argument types. Like in this case, we're saying that for whatever reason, maybe we use bar inside of function foo that for if you call bar with X, that return type, whatever it is, must conform to concept C5. So there's a number of different ways you can constrain things with concepts. And one of the kind of most useful tools for constraining functions with concepts are creating overload sets. So when we create overload sets, we can constrain the types used in templates. And this is where we get into, you will see later, there's kind of the old fashioned technique I mentioned earlier called SVNI, or substitution failure is not an error. And instead of the basically difference between the concept techniques you'll see and SVNI is about making certain versions of the template disappear if they're not valid, versus just saying this template only works if it's valid. And that kind of inversion makes it a lot easier to just design your overload sets and work with them. So for this discussion of overload sets, we're going to look at a simple example of a function that's going to divide something in half. So our kind of starting point is that we have three non-template functions for floats, doubles, and long doubles that are going to take their argument type, return their argument type, and just divide it by 2. And you'll see that these being not a template will be chosen in overload resolution before the template. And then we also have this templated half. So if it's not a float double or long double, the implementation will fall back on instantiating this template. And you see this logic here is to do some rounding for the case of integers. When you're dividing by 2, this will do the rounding. But so this will be taken for everything that's not a floating point number. This will be taken for everything that's a floating point number. But what if in this first example we pass a string in here? We're going to potentially have trouble. So we can maybe have another version of this that puts everything into a single function. And here's where constexpr shows up again. This is constexpr function half. And we have this context for if, which means that only the first branch will be instantiated in the function if the condition is true. Otherwise, the resulting condition will be used. And so now we can kind of constrain this. So we'll use our integer rounding technique. For instance, that probably should be using the unsigned integral concept there. Thank you. No one called me out on that the last time I used these slides. And then, if it's, as Francis points out, we should be using the T as unsigned integral concept. We'll do that rounding math. Otherwise, we'll do the divided by T. And again, maybe we could also, instead of using the constexpr if, another option is using overloads for again, this probably should be unsigned integral and floating point. And there's kind of another variation is, well, what if it's not just built in unsigned or which really probably should be the right thing, or floating point types, but what if we have some arbitrary user type that also can do divide by 2, like perhaps SIMD instructions or some other operation? The way we can do that is we can, here's where we're going to add our own custom concept to the picture. And so this is our first example of this. And so you'll see we have this can-half concept that's being used to, instead of having a class T that is used in these functions, we're going to have this can-half T. And the way this works is the can-half is going to define this requires clause that, and actually, excuse me, I get the mixed up the names requires clause and requires statement. But this is saying that for some T that's of that type, that this expression is a valid expression, that we can divide it by 2 of that type, and that it will return the same type. And so what this allows us to do is have our 2 overloads for things that are what should be unsigned integral, other things that can be divided, and then just anything else that can be divided in half normally, we'll use the bottom expression. So when we made that requires clause, I want to show another example of that, and to watch out for kind of one easy mistake that can be made. In this example, you'll see the requires clause is a bit more complex. And this is a silly example from kind of an early draft version of this talk. And what I was wanting to do here is define some concept, and don't ask the reason why. The reason why is only for doing silly concept demonstrations. But this concept is something where We want to be able to concatenate something with a plus operator, and that the return type, that the two arguments that we're adding are going to be the same type. And we want to make sure that they're not arithmetic types. And we can do this, design this concept like this. And the important thing to watch out for is the use of the requires keyword inside of this concept when we're naming these other concepts, or saying that we require that the two types are the same. The reason for that is, if you did it this way without the requires clause, this might not be doing what you're actually thinking. Instead of saying that the first line in orange, that the decay of T and U are the same type, it's just saying that it's valid C++ to put T and U, or decay T and U into same as. Same thing with the not arithmetic V. This is not saying that that statement is evaluating to true. It's just saying that that's a valid statement, which is why we need the requires keyword to actually say we require that concept, or the second two, that type trait, evaluates to true. And the way you can avoid making this mistake is when you're developing your concepts, if you're making your concept a subsume other concepts where you're saying you're combining some expressions like the A and B, and then saying, yeah, concat plus must have this expression be true A and B, and then also must have these other concepts be true. Instead of putting them inside of this requires expression with the requires keyword here, if you put it on the outside and say concat plus equals are same as, and not arithmetic T, and not arithmetic U, and requires that A plus B, if you do it this way, you're not going to risk making that easy mistake of leaving out the requires keyword there. And the rules about how the compiler determines which template is more specific when it's choosing an overload are quite complex. But my understanding is that they are using kind of the seeing which templates are which concepts are common between the two. And I believe this also might help avoid some ambiguities in certain circumstances, but the rules are complex, so don't quote me on that. So one of the, in addition to kind of being able to constrain overload sets, one of the other really nice things about concepts is being able to use them as API documentation. And so for this example, this is going to be our kind of first audio example. We're going to talk about a concept called an in-place processor, and I'll show what that means in a minute. And this processor is going to come up through the rest of the concept example in this talk, as well as a brief concepts and TDD example I would plan to do at the end. So in this discussion, what we call an in-place processor is going to be some type. In this case, we have this struct inverse that is going to have a process function that takes a span of floats. And this is very common in digital audio processing, that you'll have processors that have some common signature like this. It normally won't be a span of floats. It might be something more MD span like that, usually is homegrown because MD span is new, but we usually have some multi-dimensional span like things. We might have multiple channels of audio, like one span of audio for your left ear of your headphones and the other span of audio for the right ear of your headphones. But to keep things simple for the talk, we're just going to assume we have a single span of floats we call this process function. And so our concept that we're going to build up is going to be around things that have a process function of this form. The other thing to keep in mind is some processors might have a reset function. So this one, if we look at what it does to our buffer that gets passed in, it will transform it using standard negate. So it will essentially invert the polarity of all of the data members from positive to negative and vice versa. And there's no need for state in this function because it's just operating on each individual value. But this class, for example, that also has a process function, this is an example of a simple digital filter. And if you look inside the process function, you'll see that it does a calculation that is dependent on keeping track of one previous value to operate on. And so there's some state that we need to maintain per call to process. And so often in our digital audio applications, processors like this will need to have some reset function to reset them back to their default state. So for example, if you were to process one audio file with it, you'd want to start back at your default state before processing another audio file. And so now let's look up how we can start building up a concept for something like this. So we're going to think about this example of something made up class, but things like this do exist in our production scenarios that we're going to call a wrapped processor. And this wrap processor also has a process function like we saw before that takes a span of floats. And you'll see what it does is it calls some preprocess function that does some pre-processing stuff, then calls process on some internal processor object that it's managing, and then calls some post-processing function to do some final post-processing on the data. And you see this is a template on the class processor type that allows us to take any processor type in our constructor. But for this to work, because we have our process function be called in process, the process type must actually have a process method that takes a span of floats, and we put this in a documentation comment. So we hopefully make that easier for folks to know, hey, you have to put an in-place processor in here with this kind of process function. You can't just call this with some string type. That's not going to work. We could maybe improve this for the comment instead by adding a static assert, and we can make some custom type trait to say, okay, we're going to have a static assert if the type you're using with this class is not what is in place processor B equals true. And this is what you'd have to do before concepts to make a type trait like this. I'm not going to get into all the details, but I'll just kind of point out kind of the scary stuff. So in place processor V is the templated const for Boolean that we use this meta function like we saw earlier, where we call that function with T and it returns some value. And again, we have some stuff above that are our two specializations, and we'll see if this is all true or false. We see stuff like class equals void. So we're having some type that is void that we don't care about up there. We have false type and true type, which, that's probably true or false. That, I think we understand. And then we have this big thing with what's a void T? We've got decal val, then decal type of this decal val. Like, what's all that doing there? Hey, you know what the great news is? We don't need to worry about that, because we can, instead of writing a type trait like this, we can make a concept. And doesn't this look so much nicer and easier to understand? The concept that says for some class T, we require that if we have a T called P, then we call process on that P, passing a span of floats. And so isn't that so much nicer than doing this? And so once we have our concept like this, we can then pass it to our in-place processor, and now say that our wrap processor doesn't take some arbitrary class processor type, but that processor type must be an in-place processor. But one thing look at next that we might run into trouble about is, what about this reset function we're calling on processor? Because if we look back at our concept says in-place processors must have a process function. They don't say anything about in-place processors must have a reset function. So clearly, this is only going to work for in-place processors that happen to have a reset function. So it'll work for our one-pole filter that we showed earlier, but it won't work for our inverse. And this is something that was talked about a lot as one of the kind of disappointments people had with C++20 concepts when they came out, is that the compiler itself doesn't prevent you from making this mistake, or whether it's a mistake or not, but cause of a potential instantiation error where you constrain your processor type to make sure you can call process, but you're then calling other functions on it that aren't part of the concept. And if it works, it works. And if not, you get back to your old-fashioned ugly compiler errors. So we'll look at how we can address this problem. One way is, again, using our if const expr expression to write some code that will only evaluate if something is true. And we're going to put in this if const expr expression, this requires, that is kind of like a inline concept. We're not naming any concept, but we're just saying we require that for processor type named P that we can call reset on it. And so this if const expr block, when this class is instantiated with something that has a reset, it will exist. And in places it won't exist. One thing to mention, I would avoid whenever possible explicitly writing out kind of inline requirements like this and instead create name concepts. There's kind of two advantages of this. One, again, with the compilers deciding what concepts are more specific than others, when it considers two concepts as the same concept, it's if they exist in the same source location in the translation unit. So even if I were to write this requires kind of here and somewhere else exactly the same, the compiler would actually think of them conceptually as two different concepts and would be able to see that, oh, they're kind of the same in determining what's more specific. Also, if you're using these requires clauses just to inline like this on like a template parameter of some class and you're writing out of line definitions, it gets really verbose. So later, when we get to our TDD example, we'll see how we do reset with a name concept instead. One other option is this example will allow the wrap processor to have a reset that will be safely called on any processor that doesn't have a reset, that does have a reset. And then if there's no reset, it'll be a no op. But another variation is if we want the wrap processor to have no reset function and instead just, if the internal type has a reset, it has a reset. And if the internal type doesn't, it doesn't. You can instead put the required, not use the if context spur, but if after the reset we say requires, our dot reset, uh, then in that case, this whole function will only exist if the reset exists. And the reason you need requires is I could also say like requires some named concept. And so the first requires is saying we have a concept requirement coming, and the second requires a kind of inline concept expression. So we'll look at another example of how concepts can be used for documentation. We have the block. This is another thing that we're going to call block processor. And this is something that's going to take some buffer of input, some buffer of output, and some function. And what this is going to do is apply this function on the input and put the results in the output. And to make this work with arbitrary functions, the kind of the most simplest thing you can do is use a standard function. But in real-time DSP, this is probably not what we want to do because this could potentially allocate. I'm so curious what funny pictures are happening in Discord. Turtles. Yes, it's turtles all the way down. So this could potentially allocate, which we don't want to do on a real-time DSP thread. Usually we would actually write this like this, where the process function is templated with perfect forwarding. But now, as we saw before looking at other examples, there's no guarantee we're not passing standard string in here. We need something that we could process a span of floats with. So instead, we could constrain our template by saying that process function is something that is invocable with a standard span of float. And so this will be anything that has a call operator that we can call with a span of floats. And so now we can't accidentally call it with a string or a double. And maybe make it even nicer. It doesn't even have to look like a template. If we put the concept right by the type name with auto, this is a template, but it doesn't actually look like it. So now let's that we've looked at kind of how concepts can be made and used, let's look at how they can make template metaprogramming a little bit nicer. I'm going to bring up some examples from a talk I gave a number of years ago at CPPCon about a GUI library project that I worked on, and how with some template metaprogram, we were able to wrap a system that had runtime error checking with something that was compile time safe. I'm not going to go into all the details of that talk, but we're going to look at a very simplified example of that and see how it can be written more nicely using concepts. So the basic principle of this is designing properties of some objects in a GUI system. And for every type of property, we could define a property type by having some struct like this. So in the case of a size of something, we would say its type is float, the name of this property is size, and its default value is 100. And the way we would use this is in this class called hasProperties, that essentially what it's going to do is for you're going to pass types kind of conforming to this shape into it and in this parameter pack. And you'll see we're using our fold expression to say like, okay, for every type in here, call this function add property with that type. And notice the parentheses around this. This is kind of a trick with the comma operator and the parentheses and the fold expression to just say call a bunch of functions on some type, and we don't even really care about the return result. And you'll see what we're doing with that type is we're putting them in some dictionary where we're like storing the name and the default value. In real life, we do a whole lot of other stuff, but that's what, well, our property management system will just say we provided types and it somehow needs to get a name and a default value out of that type. And so again, if we have this like this, that all works. But what if instead of having types, constants here for name and value, what if we had a different something like title? Now, I know this is a silly example. Default value returning my button could just be a constant, but just we'll see a slightly more useful example in a second. But assume default value is a function sometimes and sometimes a constant. Same thing with name. What if you have some template property type for optional properties that takes in some other property type and says it could be, optional, and it has a name function that calls standard format to do some string formatting. So, how will we handle this? Well, we could instead make a get name function instead of just using name directly. And again, we could have our if const expr with our inline requires and say like, okay, if calling name is well formed, call return name with the call operator. And if not, just assume there's a name member and return that. But we can make it a little bit better with having a concept to make sure that this will actually kind of work out the same way. We could have a concept that it says has default value function that checks that it has some default value function. And we can have some has default value concept that checks that it has some T that's default value and its type is equal to the type of the property. And you see, we can have our two overload sets for get default value that one is constrained by has default value function, and one has its default value. And you see that can replace what we had before, where we have get name, where we were just doing T name and T default value. We now can call these functions, and they will do the right thing for us, picking the overload for either a static constant or a function to return the value. Now, what if we want to get even fancier and have something that, like, I don't really want to specify the default value because, border width, things are going to have a border of 0. Default construct float is going to be 0. So I don't even want to have a default value. So maybe I make a type like this and try to call add properties on it. Well, I get a big error message. We don't have to look at this whole thing, but this is actually an example of why the error messages with concepts are a lot nicer than with the kind of historical C++ templates. Is all of this because that shows up. So it's telling us that both these overloads were ignored because size doesn't satisfy has default value function. And the reason it doesn't is it doesn't have a default value function. And so this makes things a lot nicer to understand when you don't satisfy some concepts versus kind of the crazy template errors you'd get before. And so we can actually add another overload for get default value that is for things that are default initializable. So in this case, if we have a overload like this, our border width will happily have a get default value function that will work, and it'll just default construct that type. But that'll give us a problem for size because size both has a default value member and it is default constructible. So the compiler won't be able to pick from this or our earlier get default value that worked on things that had the member. So we have to constrain things even more by saying our generic default value is like for default initializable T's, we require that T doesn't have a default value member and doesn't have a default value function, then pick this overload and default construct it. And just for fun, what does this look like with Sphinai? So this is how get name looked from my previous talk and how we actually had to implement this in production before concepts. So get name has if const expr and these type traits. Get default value is even more complex, but luckily we don't have to do things that way anymore. So now for a little demo time, wish me luck. We're going to have some live coding going on here for a small TDD demo to show you how to get around that kind of complaint I mentioned earlier, or not get around, but protect yourself from situations where you might call functions that are not part of your concept, and kind of a workflow for using concepts with TDD. And so I'm not going to really kind of give a big talk on TDD, what TDD is. I hope some of you have heard of it, but the basic workflow we're going to do is we're going to write some code. We're going to write a test to test some behavior of a function we're working on or a class. And then we're going to write a flow, very simple code for the test to pass. And then we're going to write a new test and kind of iterate on this as we build up our class. And so the project we're going to be working on today is something that we're going to call AB processor. And again, we're going to work with our in-place processor concept we've been working with all day, that is some class or struct that processes a span of floats. And the purpose of this one, the AB processor, will be to wrap up two other processors and allow you the choice of processing through A or through B. And like a use case for this is, imagine I'm some guitar player and I want to work with some amplifier simulations, and I want to have a jazz amp sound sometimes, and other times I want a really distorted metal sound coming from this Fire Seeger amp. So I make an AB processor that has both of those, and we will be able to switch between them. And one kind of disclaimer here about this example, this could, the question came up last time I gave this talk of should we be using concepts as the interface here or templates, or should we be using virtual interfaces instead and type erasure? And the answer is both. In kind of production audio contexts, there's times where you might have a chain of processors and you don't know what they are until runtime. And so you want some sort of type erased virtual process function. There are other times when in this specific piece of the code or this specific product, AB processor will only ever be used with these two types. And so usually in lower level DSP, we're writing processors to some concept, but to use them interchangeably at higher levels, we might use virtual interfaces. But it's a talk about concepts. So that's why for our examples, we'll be using concepts. So let me switch my screen over to Emacs. All right. And so to show you where we're going, this is what the AB processor is going to look like. It's going to take two shared pointers, A and B, to some types PA and PB that are in-place processors. Don't really worry about the shared pointer. In this example, it's like, just imagine that like sometime in the outside world, we might want to hold on to other references to these to set parameters or something. But there might be situations where we take these by value, unique pointer, raw pointer. That's not the purpose of the example. Just take it for granted that we take them as shared pointers. We're going to have some function set processor. They'll take our processor selection enum A and B for picking which of the two processors we're going to use. A process function that will call either our processor A or processor B, depending which, in this case, guitar amp, we want to hear the sound come through. And then a reset function for resetting the state, if appropriate. So give me one moment to change commits here so we can get to a little bit of already written code. So let's go to our unit tests. So actually, one thing to show you first in the processor is to start off, we already had our in-place processor concept from earlier in the talk, but imagining this is the first time this concept's being invented live and I'm doing this TDD. So to start off, it's useful to just have a concept that you're going to fill out as you build up the requirements for that concept. And just so start off, we're just going to have a concept for types that is true. So it will satisfy all types at the beginning. Also, note I have this in a namespace. It's very important to have your concepts in a namespace. I've in making slide examples, I had some in a global namespace, and some very strange stuff happened. I'll give a comment on that at the end, but just put all your concepts, or maybe most of your code that in a namespace, and have a happy life. So if we look, we have some tests, and they are going to do a few things. So our first test we have is we're going to basically test that Oh, actually, I'll back up a second. So for our test, we're going to have these two stubs, one called Gen 42 and one called IOTA processor. And you'll see from the comments, the idea is Gen 42 is a processor that will output 42, and IOTA will output increasing integers. They don't do anything yet, but that's my plan about how I'm going to use them in the tests, these two subs. So you'll see we'll have our first test that is testing that when we create this, the A processor will be used at first and it will output a bunch of 42s. We then have a test that if we switch the processor to B, it will start incrementing from 0. Then the next call will continue going 4, 5, 6, 7. And then if we switch it back to A little comfort test, then we get the output from uh, the Gen 42. So getting the 42s again. So let's see where we are with our test compiling. Okay, so it should be running. Okay, some warnings we don't care about. And we see, okay, one test failed. That when we require the second call, so it was the test processor B calling it twice gives a new value, and we see that test failed. So let's see the reason why. Well, the reason why is we wrote very minimal code doing our TDD practice to get this working. So when we call process, we don't actually call any processors that were provided. We just know, to pass this test, if A is selected, I'll call fill and fill it with 42. If B is selected, I'll just call IOTA. So we actually need to fill this out with a real implementation calling a processor to get this to work. So one might be tempted to implement my stub like this to have an IOTA processor that calls IOTA and keeps some state, and then just write in our class, we will actually have some B that we initialize with our processor B. And you might be tempted to just then say, okay, I'm going to call P on MB and call process. But we're already getting ourselves in trouble because we're calling process on something that is not in our concept. And so the habit to get into to avoid this kind of mistake with concepts is we're not going to immediately use the process function. First thing we're going to do is add it to our concept. So for some T, we want to be able to call T process with the span of floats. And if we run again, oh, I forgot the requires keyword. Oops. I think that's the semicolon. Oh, I think there's no semicolon here. Sorry about this. Should have put Discord on the other window in case anyone's helping me out. But let's look at our compilation now. Okay. So our static assert failed that our Gen 2, our test stub is not an in-place processor anymore, and neither is IOTA processor because we just added this new requirement that they don't satisfy. So first thing we'll do is update our stubs. So tests will give our IOTA processor a real implementation for the IOTA. We'll do the same thing with the Gen 2 processor. And we'll call stdfill. And now those should satisfy the concept. Great. So the concepts are satisfied. We can compile again, and our test is still failing. Now that we have process as part of our concept, now we're allowed to actually use it on an in-place processor. And so now we can call process on B. And those warnings are good to remind us that we're still not using A, but our all tests pass. So we're not going to worry about that we're not using A. Time to add some more tests. So we have some more tests here that essentially these tests, and to kind of move things along, I'm going to uncomment all of this. So this test is essentially testing the inverted case of the first test. So instead of processor A being Gen 42 and processor B being our IOTA, we're going to do the opposite and make sure it still works if we swap the order of the processors. Compile and run. Anyone saw what was left over in the code? You might have a guess of what's going to fail. And okay. Processor A is used on construction. We were wanting to get 0, 1, 2, 3, 4, but we got 42s. And that's because we still have our, write as little code as possible. If it's A, just output 42s. So we got to actually use processor A. So we can add that. And this time, since we already added process in the concept, we're not pulling any dirty tricks by calling process here. And let's see what our tests are doing. Syntax error. Okay, as usual. Oh, yes. I know. Oh, okay. You got to make an A to be there. So we got our. All right, all tests are passing. Great. So one more test to bring us home. We're going to have to be able to reset the state of the processor. So we're going to have a test. This one is going to set up. So we have a Gen 42 is A and IOTA is B. We're going to pick processor B. So it's the IOTA. We're going to call process a few times, and then we will expect that it won't be our expected value of 0, 1, 2, 3, 4 anymore because we're IOTA'd our way up past that. But if we call reset and then process, we expect that we'll get the original 0, 1, 2, 3, 4 because our state was reset. So we can run our tests. Oh, there's no member named reset. Okay, so let's go along to implement reset. Okay. Looks like it output 12 through 15, so it didn't actually reset. So we got to actually implement a reset function. And again, we could be just doing this and calling reset, but we're pulling dirty tricks again and reaching into other implementations that might exist on B without it being part of the concept. So time to design a new concept. And sorry, the indentation is coming out a little weird here. I guess my Emacs config doesn't exactly know what to do about concepts all the time at the moment. But we have this new concept, can reset. And in this one, we'll say that it has some reset function. And since we're testing this about IOTA processor, we expect to be able to reset. Maybe I have a compile error somewhere if I'm getting this weird indentation, but we'll try can reset IOTA processor. And we should expect this static assert to fail now because doesn't have a reset yet. And yep, static assert failed because it does not satisfy the constraint and there's no member name reset. So we have to add that to our stub. File again. All right, back to compiling and the same failing test. Now that we added this new concept, we're allowed to have an implementation. And so we can do if const expr can reset the first processor, type PA, then we'll call reset on A. And I know that code is not under test, but this is a live conference demo. And so cheating a little bit, but this second if const expr is the one actually under test. And we call reset here if the second processor's type is can reset, compile. Passing tests. So we have now implemented our in-place processor and did not call any functions on our input types that were not checked by some concept. So the live demo over. When I mentioned the namespaces, if you want to know more about my bad experience with templates and the global namespace, check out this lightning talk from C++ on C. And one other thing I wanted to close on is just kind of an encouragement for others to consider giving lightning talks or organizing open content or applying to give talks at conferences, because you might be watching this talk live or online and think that myself or other conference speakers are some kind of magical gurus that are the ones that teach and talk about C++, but it's actually really, I think most people have something that they've learned that's interesting to share. Like this talk, for example, I wanted to learn actually how to use concepts and try out different stuff when I actually got a compiler at work that was allowed to use them in C++ 20. And so I tried a bunch of stuff, made a bunch of things that didn't work, and then made a talk to show it all. So I encourage more to you out there to give talks. My motivation to give that encouragement was by a panel discussion I heard a long time ago, organized by Include C++. If you're not familiar with that group, it's a really kind of great community. They have a Discord where if you have C++ questions, that's a great place to go to ask. And thank you very much. I'll quickly look if there's any questions in the Q&A. I don't see though. Looking at, I don't think I see too many specific questions here in the Discord. So I will see you all over in GatherTown. Thank you very much.